right, so in section 2.2, in 2.2, we are dealing with polynomials of higher degrees. Higher degrees. So in 2.1, we were dealing with quadratics, so powers of 2. So now we're going to be dealing with cubics and quartics and quintics. Okay, so polynomials of higher degrees. Okay, things to know about polynomials. So poly, again, meaning many, so many terms. So polynomials have graphs that are smooth and continuous. Okay, so as long as the graph is smooth and it's continuous, then we know it's a polynomial, which means that there are no corners, so to speak, or breaks, so to speak. So there's no corners, there's no breaks. So examples that are polynomials would be something that kind of looks like this. This would be an example of a polynomial, or maybe something that looks like that. These would be examples of polynomials, right? Non-examples, so non-examples would be looking something like this. So maybe you have a piecewise function. It's still a function, but it is not smooth or continuous. I had to pick up my pencil or my pen. Something that has a break in it, so absolute value graphs are not considered polynomials, or maybe something that just has a hole in it to begin with. Again, these would be examples of non-polynomial functions. Okay, so in the previous 2.1, we talked about the general form. So I wrote this guy out. So a of n x to the power of n plus a minus 1 x to the power of n minus 1 plus dot 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 a of 1x plus a of 0. And we say a of n cannot equal 0. Basically, this just says whatever the first, the highest degree, and what's its coefficient. And then if this was 3, then this would be 3 minus 1, so this would be a 2. So 2 coefficient and 1, and so forth. Again, this is just the general form of polynomials, not something that we have to memorize. Okay, but it is important because we are going to be speaking about end behavior. So that's what our next topic is talking about. So end behavior. And that is what the end of the graphs are going to look like. Okay, so what we're going to focus on is we're going to focus kind of on this guy right here. Okay, so this n value can be two things. Okay, so the first thing would be when n is odd. So if n is odd, then two things could happen. What happens if a of n is greater than 0, aka a of n is positive? Okay, if a of n is positive, then what's happening with your graph is it's going to look something like this, where you have your graph and the end behaviors are in blue. And then you have your graph is doing some weird thing to kind of connect these two pieces together. Okay, speaking about end behavior, right? Well, we can actually describe this end behavior as two things. Okay, so this top part would be as x approaches infinity, where's my f of x going? My f of x is also going to infinity. So this goes together, and this is part of this end behavior. If I want to talk about this specific end behavior, I can say as x is approaching negative infinity, because again, it's going negative wise. Where's my f of x going? My f of x is also going to negative infinity. So when n is odd and my a of n is greater than 0, then this is something that can happen, right? What happens if my n is odd, but my a of n is actually less than 0? So again, a of n is negative. So what would my graph would look like? So I'm just going to draw an x-axis and a y-axis. So my end behavior is going to kind of look like this. So it's going in opposite directions. And then something is happening in between to get from one end to the other. So again, if I want to describe this end behavior, I can say as x is approaching infinity. So that arrow means approaching. And then where's my f of x going? So as x is getting larger and larger, notice that my graph is kind of going smaller and smaller. So my graph is going to negative infinity. And over here I can say as x is approaching negative infinity, my f of x is going to positive infinity. So again, that's my arrow for approaching. And we can see this for any odd behaviors. So the easiest equation that we can think of, right, is a line. Right? So if let me move this over so we can see our line. So, oops, didn't mean to do that. So y is equal to 2x plus 1. So again, notice that our highest degree is a power of 1. Notice that our a value, our coefficient, is positive. And again, our end behavior is positive up here and it's negative down here. Again, kind of focuses on what this looks like. So it's almost looking like a line. If I make it negative, so let's put a negative in front. So again, notice that the end behavior kind of mimics what this kind of looks like. So if you can remember how to graph a line, then you can know how to graph anything that is a 3rd degree, a 5th degree, a 7th degree, an 11th degree. We kind of know what's happening. Okay. So we also have when our end behavior is even. So when n is even. So again, when n is even, two things could happen. So again, we're going to say that the leading coefficient, a of 0, is greater than 0. This might happen, right? So again, I'm going to have my arrows facing up. Oh, that's a bad looking arrow. Let's redraw that arrow. So my arrows are facing up. Now notice that I actually don't need to cross your x-axis in order to get to this other line, but I can. So again, maybe some interesting things are happening, and it looks something like this. Again, if I want to describe this end behavior, I'm going to say as x approaches infinity, my f of x is also approaching infinity. Over here, I'm going to say as x approaches negative infinity, f of x is approaching infinity. So again, when I describe my end behavior, I want to talk about both types of ends, so the beginning and the end of it. And then what happens if it's less than 0, right? So it's negative. So basically what this basically means is that it's going to look like this. So again, maybe I'm going up and I'm going down and I'm going up one more time. So again, as x is approaching infinity, my f of x is approaching negative infinity. And over here, as x approaches negative infinity, f of x is approaching negative infinity over here. And so what this should remind you, if this is linear, the easiest even number you can think of, right, should be a quadratic, right? So if I just say x squared. So again, notice that it's even. Notice that the a value is positive, and notice again, where is it facing? It's facing upward. So again, just like this. And then if I throw in a negative, so -2, doesn't matter. So now notice that it's opening downward, so end behavior, again, kind of looks like that. So if you can remember for the even, if you can remember quadratic as the smallest one, you'll always get your end behaviors right. And then for your odd, if you can remember linear, then you'll always have your end behaviors correct. Okay, so what I want us to do now, move this back over, is let's play a little matching game, right? So let's mix and match. So mix and match possible graphs. So if I draw, here's my A, and I'm going to draw something that looks like this. Great. Draw my B. Maybe my B looks something like that. And then I'll draw C, and maybe my C looks like this. All right, so there's my 3 graphs. And then here are my equations. So maybe this is f of x is equal to negative 4x to the power of 4 plus 2x squared minus 4. And then maybe I have a second equation, f of x is equal to x to the power of 5 minus 4x4 plus 2x squared, I'm just making up the same numbers, minus 5, right? So which ones do you think would go with the graphs? I'm just going to put 2 here so at least one of them doesn't have it. All right. So what you should have said was that the B's graph actually goes with number 1. So notice that it's even, so it should be facing either the same direction. And notice that there's a negative, so they're both facing downward. Again, we don't know where the x-axis is. It doesn't really need to focus on that. But again, we're focusing clearly on that part right there. Okay, and what about for 2? So for 2, hopefully you went with letter choice A. So again, it's positive, so our positive ones should be going kind of like a linear graph. So it should be looking like a linear equation, and that's what our behaviors would look like. So what I want you to do is I want you to come up with your own equation for letter C. So can you come up with an equation that should be letter C? There's a million different ways that you could come up with one, but just take a moment and try to come up with one right now. Okay, hopefully you pause the video. This would be my equation. I'm just going to make it really easy. I'm going to say negative 2x to the power of 3 plus x minus 1. That's it. So again, it has to have an odd exponent number, and it has to have negative because it's going in the opposite direction, unlike letter A. Okay, so there we go for mixing and matching. All right, so let's move on and now start talking about the zeros. So I do want you guys to copy this down. So it says the real zeros of polynomial functions, because we will be discussing what imaginary zeros are all about. So it says if f is a polynomial, right? So again, we're just talking about, f of x is equal to something, right? And a is a real number, right? Then all of the following are equivalent. So we're saying that x is equal to a is a 0 of our f function. We can also say that a 0 and a solution mean exactly the same thing. So it says if I set f of x equal to 0, so it means 0 is equal to whatever we put right here. We can then say it's a factor. So x minus a is a factor of your f. So again, we can factor some stuff out. And then we can also say that it's your x-intercept. Okay, so what do I mean by this? So let's do a quick example. So example number 1. So we want to find all the zeros of this function. F of x is equal to x cubed minus 6x squared minus 16x. So the first thing I'm going to do is I notice that there's an x in all 3 terms. So I'm going to go ahead and I'm going to factor that out. So I get x squared minus 6x minus 16. And then I'm going to go ahead and try to factor that out one more time. So negative 16 and negative 6. So 8 and 2 are a number, so that means negative 8 has to be there. So again, we use our box method. So x squared minus 8x, positive 2x, negative 16. So x, negative 8 and 2. So this becomes x and x minus 8 and x plus 2. So again, notice right here, these are all of our factors, x minus 8, x plus 2, and x. So if I go ahead and I set this equation now equal, and I'm going to set all my factors equal, I will get my answers. X is equal to 0, 8, and negative 2. So again, those are all of my zeros or my solutions. I can also write them as ordered pairs, 0, 0, 8, 0, and negative 2, 0 as x-intercepts.